baseline techniques, which are orthogonal multiple access. The two prominent ones are TDMA and FDMA in the current wireless deployments. And for non-orthogonal multiple access, we proved basically that this increases the sum rate capacity and can reduce the outage probability in our studies. Okay, so let's first talk about OMA, or orthogonal multiple access. So from a time frequency resource perspective, the way it can be thought of is having, as it says orthogonal, you have orthogonal resource allocation per user. So basically, they're in the two types. There's TDMA, which is time division multiple access, and each user has its information scheduled in orthogonal time allocation. So as you can see here, over a certain shared bandwidth, the users will have their information transmitted in orthogonal time slots. Whereas in FDMA, it's frequency division multiple access, and in this case, the users all are have their information allocated over the entire time resource, but they are allocated in separate frequency resources. So the big problem with orthogonal multiple access is basically it's very inefficient in terms of resource utilization. And that's why NOMA has garnered a lot of interest in the past few years as an alternative to for future wireless system deployments to improve the spectral efficiency. So from a system perspective, we can look at the Downlink NOMA system as a base station. So a base station would serve multiple users, and what happens is that the information of all of these of the users that are going to be served go through an encoder and a mapping, and rather than assign each one of these users its own time or frequency orthogonal resource, what the base station does is it assigns the information of all of these users to the entire time frequency resource at the same time and over the same frequency. So that's accomplished by what's called superposition coding, and that entails to basically go through what's basically the legacy encoding and mapping of the information onto the time frequency resource, and then the extra step is to combine, to basically put the superposition of these signals together and then transmit it to all the users. So basically all of these signals are superimposed on each other and interfering with each other, and they have to share the power allocation. So the antenna has a certain maximum transmit power, so the base station will have to divide the transmit power amongst all of the signals. The signals go through their wireless channels to each of the users' antennas, and the users have to use what's called successive interference cancellation in order to remove this interference and ultimately extract their own information from the combined signal. So from the transmitter side, superposition coding, the way it can look is if we look at the same time frequency grid, instead of having the information in orthogonal resources, it's just kind of all blended together over the same time frequency resource. So if we just think of a two-user example, at the symbol level, you have what's called a quadrant amplitude modulated constellation. And typically, if it's orthogonal, within one resource, you will see only the 4 constellation points in the case of 4 QAM. But in this case, because there's a superposition of 2 signals, and one of them has greater transmit power than the other, you have the 4 main constellation points of the larger powered signal, but then the 4 smaller constellation points of the signal with the smaller power. So the actual constellation points that are seen by both receivers of this signal are these 4 here, or these 4, or these 4, or these 4. So the big key is that the receivers first see these constellation points at the macro scale, and then once they would remove those, then they can see these smaller ones. So let me show that in the next slide. So successive interference cancellation. So this is the procedure of detecting the signals with larger received power first, and then those are detected, decoded. The code words are checked through the cyclic redundancy codes and all these error correcting code procedures to verify that they're the correct code words. And then once that's verified, that is sent back into what's called a successive interference canceller, and that signal is regenerated in order to then subtract it from the received signal. And therefore the new signal that is the output of this successive interference canceller is that the summation of all those signals minus the first signal, and so on. And so the signals, in order of beginning from the largest transmit power, in order of decreasing power, are removed until the desired signal is achieved. So if we look here at the constellation view, suppose this is the symbol that was received for the first signal with the larger power. So once it is determined that this is the symbol detected, then the receiver goes on and determines the second signal, and it will decide between these four, and then it can ultimately decide that this one, for example, was the second detected signal. And once the signals are detected, then they can be decoded. Okay, so basically, as you can see, the key to NOMA is the power allocation strategy. So if these signals transmit powers are too similar, then the constellation points, so if you go back here, these constellation points cannot grow too far. If the amplitude of the second signal is very large compared to the first one, then these points may end up leaking over here or over here, and so on. And that would lead to the case where a lot of errors would be caused by these interference signals, and they would not be able to be removed by the successive interference cancellation. So that's why we focused on power allocation strategies in this study. So in these studies as well, it is assumed that certain procedures like channel estimation, signal detection, decoding procedures, those are all performed ideally. And when we mention the channel capacity, the information capacity, it is referring to the Shannon capacity of the channel. Okay, so moving on to fair power allocation approaches to downlink multi-user NOMA. So the motivation for this study was to determine whether not only can NOMA outperform OMA, but what is the exact performance gain in this case? So in this case, if we look at the most ideal scenario where the base station knows the exact value of the channel gains for all of the users, how much can the performance increase? So initially we go to the two-user case. So two-user NOMA means that just two signals are superpositioned at the transmitter, and then at the receiver only two signals need to be resolved. And for the first case, we look at random user pairing, and then go to opportunistic user pairing, where a cell edge user and a cell center user are paired. And then the last case, we look at the scenario where a general multi-user NOMA, downlink NOMA, is explored. So the assumptions here are that the channel has an exponential distribution in the SNR gain, and the OMA model that is used is the TDMA model with equal time slots, which is equivalent to the FDMA of equivalent bandwidths and power allocations. And the analysis is based on single input, single output antenna systems, but the concepts of the power allocation can be readily applied to MIMO as well. Okay, so let's see. I think we've already gone through some of these assumptions here. And the last one here is that the user indices, so the users are ordered from in order of increasing channel gain, and that will also be the order in which the successive interference cancellation decoding procedure occurs. Okay, so the system model in this case, as we talked about, is for OMA is equal transmit time periods. So the total transmission time is basically 1 over k of the entire time resource. And fair NOMA seeks to improve the information capacity of NOMA over the information capacity of OMA. So we have this inequality here. And in this case, like I said, the channel gains are ordered from lowest to highest in terms of the indices. Okay, so for the two-user case, since we established that if we have user 1 and user 2, then user 1 will be the user with the weaker channel, user 2 will be the user with the stronger channel. So in this case, the user 1 signal will be allocated more transit power, user 2 will be allocated less, and we define A as being the power allocation coefficient for user 2 signal. So then in this case, comparing just the equality cases of the capacities. So if the NOMA capacity for user 1 is equal to the capacity for OMA, then this power allocation coefficient has this value here. And likewise, if we equate the capacity for user 2 in NOMA to the capacity of user 2 using OMA, we arrive to this value here. So we call these A inf and A sup, which refers to the infimum of this set and the supremum of this set, which we refer to the power allocation set for A. So the power allocation set, given this, we have the following result. So as you can see, these power allocation coefficients are functions of the channel gain. So if you look carefully at these functions, as the channel gain increases, these infimum and supremum actually decrease in value. So what this theorem says is that despite the fact that the power allocation will decrease for one of the users, the sum rate capacity for this power allocation approach, no matter what power allocation is selected in this set, will always increase with respect to the channel gains. So in other words, there's never a loss in capacity for using this type of power allocation approach. So the next thing to determine is the sum rate gap, the capacity gap. So this next theorem basically says that there is a 1 bit per second per hertz expected capacity increase when using this power allocation strategy, regardless of what the value of the power allocation strategy is, as long as it is selected from this fair NOMA power allocation set. So that's pretty important in the sense that what we're saying here is no matter what happens here, that in the aggregate, there's always expected to be this 1 bit per second hertz. If this is for example, a bandwidth of 5 megahertz, this could be something to the tune of additional 5 bits per second or something like this. So the next thing we cover after going over the sum rate increase is the outage probability, where the outage probability is the case when the users have a service requirement, and if their channel is not strong enough to meet the service requirement, they are in what's referred to as an outage case. So in this case, we wanted to determine what the outage probabilities are and how much better they are compared to the OMA case. So after finding that, and my apologies for not including those expressions, they're pretty hideous, they're like 3 lines each. So, but what we found is that the outage probability actually, for the user with the stronger channel, is increased by about 2 dB. So even at reasonably reasonable values of SNR, it's roughly 2 dB, but for the user with the weaker channel, when using NOMA, the increase can be to the tune of up to nearly 7 dB. So this is a significant amount, right? I mean, 7 dB is more than, what, 4 times the transit. So a quarter of the transit power can be saved almost to achieve the same performance. And in this case, outage probability, if there's no outage, that means that the more you avoid outages, the more efficiently you're utilizing the spectrum, right? Because if there's an outage, you can have a transmission that is basically wasted at the receiver. They're not going to decode it. Likewise, the summary capacity, we can see here that just as we derived in our analysis, once the SNR reaches a reasonably high value, the capacity gap is equal to 1. So if you look here for the OMA user 1, if that switches to NOMA using the most power allocation that user 1 can use, then the gap is 1. Likewise, if we try to allocate more power to user 2, the gap for user 2 is also 1. Okay, so next let's go to opportunistic user pairing with fair NOMA. So the reason why this was an interesting topic in this study was because the main focus initially on NOMA was with this opportunistic user pairing a cell center user and a cell edge user for downlink transmissions. So the claim was that this is the scenario where the most gains are seen in performance with NOMA compared to OMA. The more similar the channel gains are, the less gain there is in using NOMA over OMA, which, if you're going to move from a baseline technique to a new technique, you want it to be used and deployed in the sense where it's going to give you the most performance gains. So, looking at this case, we wanted to come up with the exact sum rate capacity improvement when using NOMA. So here we have this theorem. It's very wordy, but long story short is that we found that at high SNR, when we use the supremum of the fair NOMA power allocation set, the expected value of the sum rate capacity increase is given by this expression here, which I won't read for you. It's kind of hideous looking, but one thing that's important to note is that in the theorem we specifically used the supremum of the set. So why did we not use the infimum? Is because if you remember from the definition of the power allocation set, the infimum is a function of the channel gain that is greater. So if we're using opportunistic pairing, then these cell center users will have a much stronger channel gain. So that channel gain value will be very large. This A infimum will become very small, combined with assigning the remaining power of that to the weaker user. So the weaker user with the very weak channel gain will have a disproportionate amount of the transit power. So basically, you're assigning a lot of transit power to a very weak user at the cell edge. So we demonstrate that in the following plot. So aside from the sum rate capacity, we also had a reasonably tight approximation of the sum rate capacity gap for using the infimum of the set. So here the red curve demonstrates the result from using the supremum of that fair power allocation set. And then the blue curve is demonstrating the result of using the infimum. So as you can see, as the total number of users in that cell increases, that performance gap using the infimum of the set begins to degrade. And again, that's just a factor of the closer that a weak user is to the cell edge, the higher likelihood that its channel condition will be very poor. So the final part of the study is the multi-user fair NOMA power allocation. And the main purpose here is a lot of studies were just assigning constant values to these power allocations, especially as the numbers increased. And then when they weren't doing that, they were using algorithms. We wanted to determine theoretically, is there always a case, can we always find a power allocation strategy that will improve the capacity of every single user in the network? If not, it should at least be at the baseline level of OMA, if not better. So using these definitions and these expressions of capacity, we came up with the following theorem, that the fair NOMA power allocation strategy from the above will always exist. In other words, there always exists a power allocation strategy that can improve the summary capacity of NOMA over OMA without sacrificing the capacity of any of the nodes compared to OMA. So we demonstrate that here by showing the sum of the power allocation coefficients, which should always be equal to less than or equal to 1. And for the case when we are improving the sum rate capacity and the capacity of each user, the amount of power allocation required is this solid line here. And it is always below 1. And for moderate values of SNR, it actually dips reasonably below. But never will it be above 1. We cannot have above 1 because that would mean using more than the maximum transit power. This dashed line here refers to the case when the base station applies just enough power allocation to have capacity equal to orthogonal local access. And as you can see, as the SNR increases, that amount of transit power in NOMA actually decreases steadily. So what that means is that the higher the SNR of the system, the more efficiently can NOMA be able to provide the same amount of capacity as compared to OMA. And mind you, it is assumed in OMA that the maximum transit power is always used in each orthogonal resource. So this would equate to a huge savings. So in summary for fair NOMA, we prove that NOMA can always achieve a greater capacity compared to OMA. And user pairing cases, we found the exact sum rate capacity gap for high SNR values. And opportunistic user pairing was shown to provide greater benefits compared to the random pairing case. So we showed that the capacity gap increases the more opportunistic user pairing is used. Okay, so the next section will be on the application of caching with NOMA systems. So in this case, the idea is that caching at the edge of the network and at users is going to become a more prominent component in terms of improving network throughput. So we wanted to investigate how can this be used in the physical layer sense, because caching has been traditionally been thought of more as a higher layer type of tool to improve the network throughput. So we came up with the idea that just like a user in a traditional NOMA system will be able to detect and decode signals with stronger transit power, and then use that acquired code word to then re-encode and ultimately subtract this signal from the superposition of the signals that it received. We thought, what happens if a user has a certain information that's cached, and that information is being requested by another user within that cell? So that's an information that a base station should know. It should know the caching behaviors and the caching assignment at a user. So therefore, if there is a user that is requesting a certain information and another user has it cached, we thought we should investigate the case when those two users are paired in a downlink transmission using NOMA. So here we have an overview of this case. As you can see, here's this user M has cached this code word, and this user is requesting that same code word. So at the receiver, depending on which user it is, if it possesses the cache, in the interference cancellation procedure, it can simply use the cache and send it to the interference cancellation block, and from there, the combined signal has this information subtracted, and then out can come a signal without the interference caused by what this code word being transmitted over here. So it's essentially an interference-free channel for that user. For the other user who does not possess the cache, this user should go the traditional detect, decode, re-encode, and successive interference cancellation step in order to obtain its own message. Okay, so for this study, the main thing that we looked at was outage probability in order to investigate it. So here we have defined some outage probability events. Sorry, some outage events, not probabilities. So we've defined some outage events, and these outage events are functions of the target rates of the data that are being requested, the power allocation A, and the transmit SNR C. So based on that, and based on these outage events, we come up with the following proposition. So basically, if the ordering of these, if these outage events are subsets in this order, so basically if the NOMA outage event for user 1 is a subset of the OMA outage event, and for user 2, the outage event of the successive interference cancellation stage is a subset of the outage event for decoding its own signal, and if that is a subset of user 2's OMA outage event, then we come up with the following power allocation set. And as you can see, this power allocation set is only a function of the target rates of the two users, rate 2 and rate 1. So based on that proposition, we were able to determine where is the operating point of that power allocation that we want, and we figured the next thing is, can we find the optimum power allocation coefficient? So in order to minimize the union of the outage probabilities. So why the union of the outage probabilities? Because the main goal here is that if one of these users in the NOMA transmission has an outage, then this NOMA transmission has failed. Because essentially the base station has wasted half of the resource, right? So the goal is that we want to minimize this union outage probability of all of the transmissions that are sent. So of user 1, of user 2 decoding user 1, and of user 2 decoding its own signal. And we came up with a very tight approximation to this optimum power allocation coefficient that minimizes this outage probability. And it's given by this very monstrous equation here, which actually doesn't even fit on the page, but we can see it inside lemma 1 of chapter 3 of the draft. So to demonstrate the results of this brief study, first, we compared the outage probability for a certain operating point of the SNR, and we wanted to see how the union outage probability fares as a function of the power allocation coefficient, and we wanted to demonstrate that there is indeed a minimum value within this power allocation set. So the set here is defined as being between this value here and this value here. So if we look back at the proposition, that corresponds to this value and this value. So the power allocation coefficient should come from between these two, and as you can see, there is a minimum right here. And if we are outside of this range, the performance degrades. Going this way, much higher outage probability, and going this way as well, it approaches 1 once we increase the power allocation coefficient too high. So we figured then, how close is our approximation of the optimum power allocation coefficient that minimizes this outage probability, the union of the outage probabilities. And so if you look at here, this solid line is the theoretical search of this minimizing power allocation coefficient, and then these blue dots represent the approximation to that to this this optimum power allocation coefficient. So it's very close. I mean, they clearly overlap and follow the same trend. And as we could see, the gap between the cache-aided NOMA system and the regular NOMA system is roughly 2 dB for this case. And the gap between NOMA and OMA and cache-aided NOMA and OMA is significantly higher. So this is over 10 dB. So that's a savings of for the same operating point. Suppose that the target is to have a 1% outage probability. Then the amount of transit power to just achieve that same or received SNR is another good way of looking at it. The received SNR is what is that? It's like roughly 12 dB. So that could be, geez, is that like, I think 1,000, 10, it's like, yeah, 10 to the 4 less transient power than would be needed here. So in other words, what happens here is this is much more robust to fading and shadowing effects that can occur in wireless systems. So in conclusion for this study, the interference cancellation using caching was demonstrated, and we showed a system model of how it could be implemented at the physical layer. And we showed that the more power, that using this, more power can be allocated to the user without caching in order to aid in the success of interference cancellation and also improve its own outage probability once it has performed the successive interference cancellation. And that can happen without degrading the performance to the user that possesses the cache. And we found the union outage probability, and we saw that it could be minimized by intelligently selecting this power allocation coefficient in the set. Okay, so the last section here is on the fundamentals of power allocation strategies for downlink multi-user NOMA with target rates. So in this study, the main motivation is this, is in a downlink system serving multiple users, in typical system deployments, it is very unlikely that a base station will possess the exact values of the channel gain. There's a lot of channel estimation, feedback channels that must be sent, and ultimately by the time the scheduled resource arrives so that the downlink transition happens, the channel estimation has degraded, has become outdated, especially in the feedback. So the receiver can always keep an updated estimate of a channel, because even in its own when it receives the downlink transmission, there's always a reference signal that is used to estimate the channel contained within the information. So the user equipment can always get that channel state information that is almost to the ideal case. It's very close and can perform these receiver processes. But the base station cannot assign the power allocation, as in the case of fair NOMA, using the channel gain. So in this, for these reasons, the outage probability is the metric, the performance metric that is used in our analysis to derive the improvement of the spectral efficiency by way of designing the power allocation coefficient. So as we could see here, what I just described about this, the acquisition of the channel state information at the base station, and then the subsequent downlink transmission of the information, is there's, as the number of users increases, and each one of them has their uplink, sends their channel state report back to the base station in their dedicated resource. A certain number of resources are used, and then there is a time gap for the base station to determine the appropriate resource allocation for this NOMA group. By the time the downlink transmission occurs, if that base station uses those channel gains, that to design the power allocation coefficients, then there is a very high likelihood that there will be outages happening because these power allocations in effect will now be outdated as well. So instead of that, we decided to look at something else that the base station always has, which is the target rate of that information. What is the transmission rate that that information requires? And that is used to design the power allocation strategy. So in this study, we use a generalized TDMA system. So rather than, compared to the one that we use in Fair-Noma, in this case, the transmit time durations are not equal. So we assume that there is some optimum resource assignment used by the base station and in the OMA system. And based on that, we have determined that this is the outage event for the OMA system. Notice this ratio, R sub n, which is the rate, the target rate for user n, divided by the time duration of user n. That this ratio plays a central role in the subsequent results. So the NOMA, successive interference cancellation decoding order. So for now, we will say that the decoding order at the NOMA receivers will be in order of increasing ratio of R sub n over tau sub n. So one thing you may wonder is why is an OMA parameter here involved in the power allocation design? Because the main goal is to improve NOMA with respect to its performance compared to OMA. If we don't make that comparison, then it doesn't make sense to replace the baseline approach to this new approach. And initially, this selection of decoding order was intuitively done, but there's actually a far more, a stronger reason that is demonstrated later. So as you could see, these outage events in OMA increase exponentially like this. So it makes sense that it would be easier to decode the ones with lower outage and remove that interference first. Once we remove those interferences, we can then decrease this for the other users. So the first result of this study was that we found that for any signal in this NOMA system where there are multiple users that are going to be decoding, there is a certain non-zero outage probability of every successive interference cancellation decoding stage. So we found that if the interference coefficient at any one of these stages exceeds this threshold, so 2 raised to the summation, to the minus of the summation of the target rates from 1 all the way to n, if it exceeds that threshold, there is no channel strength that can ever overcome that interference. Because ultimately these are interference channels, and interference channels are interference limited. So this is a very important result. This is a function of the target rates by itself, which means that the base station can know that there should always be this threshold for how to design the power allocation coefficients for a certain user n. So based on that, we have defined some of these outage events for the NOMA case, and we come up with this proposition, what's called a well-behaved power allocation strategy result. And if the power allocation coefficients A sub n follow this behavior, given by this expression in the proposition, then they will be what we call well-behaved. What well-behaved basically means is that the outage events increase in threshold as this decoding order increases. So in other words, the signals decoded first have the lower thresholds, and the signals decoded last have the higher thresholds. That's important because in this case, there's not power allocation that is wasted without improvement to performance. So based on that, we've defined some parameters. I think we can skip this slide for brevity. And we go on to some of the main results here. So theorem 1 says that the power allocation strategy such that the outage probabilities for every single user in the downlink NOMA transmission has the same probability as in OMA always exists. So there's always this power allocation strategy that can at least give you the same outage probability performance per user in NOMA as the baseline OMA system can achieve. What is that power allocation strategy? It is given by this coefficient for user K, which is the user that is decoded last. And for general N, it is given by this expression here. So as you can see, it's a function of the target rate of its own information and the target rates of the signals that are decoded after user N. So why would a user N have a coefficient that is a function of a target rate of a signal that will not be decoded? Because that is information that is not received, so then that power allocation coefficient must compensate for those signals. So it makes sense that those target rates of those signals that are decoded later would factor in here. And this gives us the following corollary, that this decoding order that we initially proposed is actually proved to be the most energy efficient. Every other decoding order will use more transit power. In other words, these coefficients will be greater if we use a different decoding order. So based on that, in order to improve the outage probability over OMA, we came up with a certain result that described the behavior for how to theoretically increase the power allocation beyond that baseline OMA strategy that we have here. And based on that, we come up with an example strategy for utilizing all of the transit power in order to improve the outage probability for all of the users using NOMA compared to their OMA outage probability. So here, in this study, we used two different channel models just to demonstrate that the robustness of this approach of these results. They're not limited to just one channel model or one scenario. We wanted to show that these are in general true things. So for the first case, this is the same channel model that was used in our first study. And as you can see, this is a plot of the outage probability versus the interference coefficient. And this is demonstrated over the different decoding orders for a 4-user NOMA. And in this case, a 5-user NOMA. And in this case, no matter how strong the channel or which user it is, even if the user that has the strongest channel, it can still, once it reaches that interference threshold, it cannot overcome that interference. The outage probability is 1. And this is demonstrated again using a MIMO channel model with the optimum detector at the receiver. And even in this case, you can see that the outage probability, regardless how big the interference coefficient, is very low. And then as soon as it approaches this threshold, it immediately goes to 1 in our simulations. And that's for the case of all of the decoding in this decoding order. For these second two plots are with respect to demonstrating the improvement of NOMA over OMA. And as you can see, user 1 in this first plot has the largest gain in outage probability compared to OMA. That's at roughly 7 dB. And then as the decoding orders increase, those users begin to experience less gains than the users that are earlier in the decoding order. But the gains are still there no matter what. Like there will always be an improvement of NOMA outage probability over OMA. For the second channel model, we see the same thing. And in this case, the ordering of the channels doesn't really matter. As long as we follow the decoding order that we proposed, we see that these gains of NOMA over OMA are exhibited. The last figure is to demonstrate the behavior, the well-behaved power allocation strategy phenomenon. And in this case, we can see that the outage probabilities in increasing order of decoding of the SIC decoding order, that those that are decoded earlier have the lowest outage probabilities. And then by the time you reach the last decoded signal, those are the ones that have the highest outage probability. But even then, as we saw, this outage probability for a certain user is still lower than the OMA outage probability. And then we demonstrate the same thing here for the second channel model. So in summary for this study is we proved that there are these fundamental relationships between the target rates of these downlink systems and the outage probability performances that can be achieved. And we showed that without using the channel gains, with just using the target rates and the baseline OMA system model, that there can always be a design to power allocation strategies that can improve the performance of NOMA over OMA. And we also showed that there is an optimum way of selecting the decoding order, which also affects the amount of power allocation to each signal. So that ends that section, and so I guess we've reached the end of this talk. So in conclusion, the three main studies that were done in this research were FAIR NOMA, which provided the theoretical starting point for analyzing the upper bounds of performance that could be achieved over OMA. And from there, we moved on to demonstrate that this can be combined with other technologies, such as caching, and use what we called cache-aided NOMA to further give improvements to the performance of a system. And then lastly, we came up with a practical approach to power allocation that doesn't require a very idealized situation, such as perfect channel state information at a base station being known at the exact moment of a transmission. And we showed that this practical approach is accompanied by very strong theoretical results that can be applied to any system. And we demonstrated that with 2 channel models. So I guess some future work that could be done in this topic would be to do the analysis for this generalized multi-user downlink NOMA. So what is the exact capacity gap for this general multi-user NOMA transmission? That is one of those things that's still kind of like a problem that's being looked at or maybe ignored by the field. But that's something that should be looked at. And then a comprehensive treatment of the uplink NOMA system transmission is also important to help design and standardize future wireless systems. Okay, so that's it for my talk. Sorry if I spoke fast, I had a lot of slides. So thank you for attending my talk, and if there are any questions.
So, is there any question from the audience? Especially the significant other, this is the best time for you to revenge. Not today? Okay, so I need to ask the audience to leave the